Hello and welcome to my video lesson 6.2 on the atomic spectra and the quantized model. So Niels Bohr in 1913 continued the concept of the atom, continued to invest in that and investigate the atom. In 1913, Niels Bohr introduced the planetary model of the atom. So very similar to Rutherford's model, which I accidentally called planetary model in the last video. That model, actually, Rutherford's model does not have a special name. It's just called Rutherford's model of the atom. That one is kind of like Saturn's rings, where it's kind of nebulous. The electrons are kind of floating around the nucleus, which is positive. Niels Bohr instead considered different orbits. So that's why this is called the planetary model, because there are different, planets that orbit the sun, and so you can imagine the different orbits are how far away the planet is from the sun. So the Earth is fairly close to the sun, whereas Jupiter is pretty far away from the sun. So the four inner planets, maybe you could consider those to be our first orbital, and then there's a big jump, and then you can go to the outer planets. So that that's your second orbital. So you can think about it a couple different ways, but maybe that helps you remember this idea. Planetary model has multiple orbits, and those orbits are different levels. And basically, the really important part here is that these are discrete energy levels. They are not just nebulous. They're exactly, or not exactly, but well, pretty much exactly. Like they're at certain energy levels, and those energy levels are very important. The closer that an electron is to a nucleus, the more it's being held onto, the more tightly it's being held onto by that nucleus, because the proton inside is using its electrostatic forces to pull the electrons in. Okay, the further away that the electrons are, the more easily we can ionize them. Okay, the concept was proven using spectral lines and absorption lines of different elements. So using a spectroscope, using diffraction grating basically, you can see spectral lines or absorption patterns. So if it's an element that is being excited, usually with electricity, it produces light on its own, and it's producing bright lines at certain spectrums. So you can see here the emission of hydrogen lines there. Those are all just different visible light spectrums, but then you can also see the opposite. If you send light through, like let's say from an incandescent bulb, which is continuous spectrum because it's black body, you can see, if you send it through hydrogen, you can see absorption occurring at the exact same locations, in fact. And so because this happened, Niels Bohr suggested that electrons have discrete energy levels, and we can figure out what those energy levels are because of the photons that are being produced by those energy levels. So here is the hydrogen energy level thing. If you look at the spectrum, yeah, I guess. If you look at the Balmer series, which is the one that gets to n equals 2, you can drop down from different energy levels, and you will get different types of light. So if you drop down all the way from the top here, you're going to get a very strong, powerful light, because it's a lot of energy, so it's going to have a lot of energy per photon, and that's going to be your purple. Down here is going to be your red. Now, if you want stronger than ultraviolet, all you have to do is go down here. That'll be your next one on the spectrum. So actually, this whole thing is completely set up in order of which is the most powerful and which is the least powerful photon being produced. So on this side is the higher energy photons, and on this side we have the lowest energy photons. Okay, so that's important to notice when you're going through. And if you look at the Balmer lines just happen to be the visible spectrum, but you can go past it on either end, and you can also have lines there. We just can't see it with our eyes. You would measure it with some sort of other device. And basically what he was saying is that if light is being absorbed or emitted using these electrons bouncing up and down orbital levels, if they're dropping down a bunch of levels, but it's a specific wavelength, it's not continuous, so it must be a specific drop that is causing that to occur. And that's where he came up with this idea. The issue is that this considers the electrons to exist only at certain locations, where in reality they are more like a cloud around the nucleus. So let's take a look at what that looks like. So the electron cloud model is from Louis de Broglie in 1924, and then later Edward Schrodinger added to it in 1926. They came up with the concept basically that if light can act as both a wave and a particle, maybe small particles like electrons can also act like a particle and a wave. So particles are actually waves, and waves are actually particles all at the same time. So what they did is they were thinking to themselves, well, Young's double slit experiment with light to prove light is a wave was basically like this, right? They've shown light at a double slit, a single slit just to make it all in phase, but then they've shown it through a double slit here, and it turns out that we have interference pattern, bright spot, dark spot, bright spot, dark spot, bright spot, like this. This is happening because light is a wave. You see that with any type of wave. So what de Broglie suggested, well, what if we try this with electrons? So we shoot electrons at a double slit, just like we did with light. And what you would expect is that you get two lines right here and here, directly behind, because if you were like just to shoot a ball, like a tennis ball, at two slits, you would end up with one going through there, one going through there, one through there, one through there. And it would just end up being, if you just plotted that over time, you just have two lines on the wall. But it turns out that electrons don't act like a particle when you do this to them. What happens is that electrons will actually interfere with themselves, and they're going to have this central antinode, which is very strong, and then they're going to have N1, N2, etc., just like we had with Young's double slit. So, because this, diffraction grating and interference pattern shows up with electrons as well, they suggested that electrons are actually also waves, and so they're not just a particle around a nucleus, but they are waves around a nucleus. So you can kind of see this idea of these standing waves showing up here around that central nucleus, or you can kind of look at it here and look at like kind of a probability heat map of where the electrons might be. So just a couple different ways of showing it. We can also maybe quickly Google if you Google S&P orbitals, you can also see different images of what those look like. So like this right here, or you can see just different shapes that kind of show up. So these are all probability things that are going on. The dumbbell, the donut. This is a probability heat map of where the electrons are going to be. This is what de Broglie was showing. So, so given all that, we're going to go ahead and try two different questions here. I'm going to zoom out one so you guys can see the full question for both. Pause the video right now, try it out yourself, and see if you get the same answer I do. Okay, so example 1. Given that the H alpha line with a wavelength of 656 nanometers, which is red, has a transition from 3 to 2, if you want to get the next wavelength, slightly shorter, which transition should you aim for? So if you're going for red, that means it's a pretty long wavelength, but it's visible. Okay, that's what we're talking about. Long, but still visible. So you can see here, this is the visible spectrum. That's going from 3 to 2. So it's going from here to here. That is our red spectrum, or our red transition, the H alpha line. So if you want to get the next color available, I believe the next color, well, we know that the next color is going to be going from here to here. So it's going from what level to what level? Well, it's going from n equals 4 to n equals 2. That would be the next wavelength. It's slightly more energy, which means it's slightly higher frequency, which means it's slightly shorter wavelength. Assuming that the energy levels are all correct here, what is the wavelength of the above transition? So this transition here. Well, the red one, if you were to do that one, would be 3.949 minus 1.51. But the green one is going to be 3.49 minus 0.85. So you can see, hopefully here, the energy that's being released in both cases. So with the red line, we release 1.8 electron volts, but with what I think is the green line, we'll see in a bit, but I think it's going to be green, 2.64. Yeah, 2.64 EV, which is what we're going to be dealing with here. So this is not the wavelength, which is what we're looking for, but this is the energy of it. Now, energy is HF, or another way to write that is HC over lambda. So we can rearrange for the wavelength, and so we get this sort of thing occur. Since we're already in EV, what we're going to do is use, I think it's this here. Let's just double check. Yes. So we're going to use this H, which is going to be the one that has electron volts, because we want that to cancel with our energy. Otherwise, we're going to have a real pain in dealing with that. But our energy was 2.64, and so our wavelength is 4.70 times 10 to the negative 7 meters. Keep in mind this is meters, so if we want to get nanometers, we times by 10 to the 9. So it's 470 nanometers. Okay, actually what I'm reading online here is that it's just at the start of blue. Which, actually if we go up here and check, that checks out. It's kind of this baby blue color that it's giving. So that's the one we just found. So maybe I write blue like this. Alright, so now let's try example 2. Example 2 says a particular experiment sends carbon-12 atoms, which tells you the mass, towards a diffraction grating. On a screen 2.32 meters away, an interference pattern is observed, which we can see in the graph here. If the speed is known to be, that's not a speed, 325 meters per second, what is the diffraction grating slit spacing? So we're working backwards and finding the slit spacing, which is kind of a weird way of doing it, but this is what we're going to do in this question, just to shake things up a little bit. So what we have to first do is kind of recognize that it's a interference pattern question. And so there's that formula, this formula here, which has to do with interference patterns. And also that D is what we're looking for, right? So let's go ahead and solve for D. So it's going to be n lambda over sine theta. This is our D. That's what we're looking for. But we don't know the theta and we don't know the wavelength, so we're not doing super well yet. But can we figure out the wavelength? Well, we can. What happens here is basically we're saying that the momentum is the momentum, doesn't matter what type of it is. So normally momentum is mv. But we also know momentum is h over lambda. And so by rearranging this formula, we should use a different color, oh well. By rearranging this formula, we are able to solve for our wavelength. So that's a good first step. Okay, secondly, this is our N1 position, which looks to be a little bit beyond a third of the way there. So not entirely clear, but maybe 0.4 millimeters. Because this is 1 millimeter over here, so, oh no, a little bit less than a third. No, a little bit more than a third. Yeah, maybe 0.4. I don't know, 0.3, 0.4, somewhere in that ballpark. Somewhere in that range. I'll go with 0.4. Okay, so we know that that's kind of the distance away that it's appearing on the wall. So if you imagine your double slit here, and then you show up on the wall, and that's the distance that it gets to. Well, if you remember correctly, this here is our L and our X, and this is our theta. So what we can do is we can actually get the theta using the L and the X, using tan -1 of opposite over adjacent. And so we can use that to get our theta. All right, so now we're going to put these different values back into this original equation. So D equals N, which is 1, but we can just write it as N. And then lambda, which is H over mv, over sine theta, which is sine of theta, but theta is going to be tan -1 of x over L. And so now we have this big long equation that can give us the diffraction grating. So n is just 1, so we can ignore that one. H, which is 6.63 times 10 exponent -34, over m, which is 1.66 times 10 to the exponent -24, times v, which is 325. Yeah, I think the number will be slightly different. I think I used, when I made the question, I think I used 3 millimeters, but that's okay. That's fine. We'll get a slightly different answer. And then, what do we have? And then it's over sine, and then tan, x, which is the spacing, which we measured to be 0.00 would be centimeters. Another one would be tens of millimeters, and then 4 over, and then L, which is the distance to the screen, so 2.32, bracket, bracket, and we get our final answer of 7.12 blah, blah, blah. So let's write that down. 7.12 times 10 to the 9, -9 meters. So if we times 10 to the 9, Yeah, this is much smaller than I originally anticipated, but that's okay. 7.12 nanometers. Considering also here, just by the way, like the error in measurement there, it's really only a 1 sig dig solution because of how poor our original measurement was. You can keep this in mind. 7 nanometers, 3 nanometers, somewhere in that ballpark is the size of the transistors in computer chips. So this is pretty darn small, but we are being able to manufacture things that are this small, which is incredible. So I wonder if there's some way of, if we could use a computer chip and do this, basically this experiment with it. Anyways, I hope this video helped you better understand both de Broglie's wavelength concept as well as Bohr's electron orbital levels and shells. I hope this video helped you understand both of those a whole lot better. Hope the video helped, and good luck.